All right, class. So today we're going to focus on reviewing a little bit of the material that you've covered the past few days here this week. What we're going to be doing to begin is adding in our understanding of double and triple covalent bonds into our structural formulas. So as you guys have seen so far, there are cases where even if we connect our various atoms in a molecular compound with single bonds, we don't have enough electrons to make our complete octet. So there are sometimes cases where we're going to need more than one pair of electrons shared between any of our two particular atoms. So one way this can be done is through a double bond, and of course the name double bond means we're going to have to share two pairs of electrons between these atoms. So again, because we're dealing with two pairs, we're going to have a total of 4 electrons there. All we're going to do as before, we represent a single bond with a single dash. We're now going to represent this double bond with 2 dashes connecting our atoms together. Yeah, there could be a case where a double bond is not enough to make sure that each atom has an octet. In that case, we might have to move up into a triple bond in which we are sharing 3 pairs of electrons for a total of 6 electrons held between the two. Yeah, we're going to represent this triple bond with just 3 dashes. So our rules for how we write a structural formula still is very much the same. We have to first figure out for each of our atoms that we have how many valence electrons we begin with. Another piece of information that's going to be useful to us is we need to know how many electrons each atom needs to satisfy the octet rule. So let's say we have something in group 15, where we're going to have 5 valence electrons. We need to then go and move into 3 more to get our octets, to bring us up from 5 to 8. Once we know the number of valence electrons for each individual atom, we want to then focus on how many total valence electrons we have. To begin our structural formula, the easiest way to do it is to take whichever atom needs to have the most electrons in order to get to the octet rule. We're going to want to put that into the center. From there, we take all the remaining elements and we're going to connect it to that central atom using single bonds. However many electrons we have, we're going to fill in as our lone pairs. Now the problem we run into that we saw a little bit on that last slide is sometimes it is not enough to make sure that every single atom has the 8 it needs, or if we're looking in the case of hydrogen, that it has the 2 electrons it needs. So if not every atom already has a full valence shell, this full octet rule, then we might have to replace some of our single bonds with either double or triple bonds until we satisfy this octet rule. So we're going to begin by looking at our example of SO2, sulfur dioxide. And the first thing we're going to say is, if we look to our periodic table, we're going to see that sulfur is in group 16. So therefore, because it's in group 16, it's going to have 6 valence electrons. So because it has 6 valence electrons, that's going to tell us that we're going to need to have 2 more. When we look at our first oxygen, oxygen is also going to be in group 16, so that means it's going to have 6 valence electrons as well. And it also is going to need 2 more. Our final atom here is going to be another oxygen. Again, has 6 valence electrons. And we're going to need 2 more. So we think about the total number of valence electrons we have here. We're going to have 6 plus 6 plus 6 for a total of 18. So in this case, each of our valence electrons each of our atoms needs to have 2 additional valence electrons to complete the octet rule. We're going to go ahead and put sulfur in the middle just for the sake of having a little bit of symmetry here. So first thing I'm going to do is put sulfur in the middle, and then using single bonds connect oxygen to the outside. So right now what we've done is we've used up 4 total electrons, right? Each single bond represents 2 electrons. So you use 4 of the 18. Now I'm going to fill in the rest of my lone pairs in that remaining 14 electrons we have. That's right. We're taking care of 4. We now added 5, 6, 7, 8, 9, 10. Sulfur already has 4 electrons, so it only needs 4 more. So you have 11, 12, 13, 14. Go over the last oxygen, we have 15, 16, 17, and 18. So now what I want to do is check to see have we satisfied the octet rule for these. So if I look at our oxygen, look at our electrons contained here, right, we have 6 lone pairs plus 2 from the single bond, so that's good. Get that sulfur in the middle. We're going to have 2 lone pairs here, so total 4 plus 1, 2, 3, 4 from our single bonds. That also gives us 8. Looks good. But as we go over and look at this oxygen here, we have 2 electrons from a single bond, and we have 3, 4, 5, 6. So we don't satisfy the octet rule. We don't have enough electrons there. So we know that we need to give that oxygen on the left an additional pair of electrons, and we'll do this through a double bond. So what we're going to do is take that sulfur, and we're now going to have a double bond connecting it to the oxygen on the left. And because the oxygen on the right already had the 8 electrons it needed, we're going to keep it just as it was before. So now since we have a single bond and 1 double bond, right, these 3 dashes we have written are going to count for 6 total of electrons. We're going to fill in our remaining 1 as lone pairs. So we're going to have 7, 8, 9, 10, 11, 12. Our sulfur only needs 2 additional electrons, so we're going to have 13, 14. Then our oxygen only needs 4 more electrons. So we have 15, 16, 17, 18. So right now if we go through and look at each of these, our oxygen here is going to have the 8 it needs. Our sulfur, because it has 6 through bonding, 2 lone pairs, that gives us the 8 we want. In the oxygen on the far left, we have 4 through our double bond. We're going to have 4 lone pairs, so that gives us the 8 we need. So that looks good. So our final answer for our structural formula is going to be sulfur is going to be attached to 1 oxygen with a single bond, attached to our second oxygen with a double bond. Oxygen on the right is going to have 3 lone pairs. Sulfur is going to have 1 lone pair. Oxygen on the left is going to have 2 lone pairs. So that would be our final answer for the structural formula of SO2. The very last type of structural formula we're going to be looking at is going to be that of a polyatomic ion. So we might remember polyatomic ions from the back of our periodic table, that chart we used when we were looking back into ionic bonds. The reason why we're looking at them now is that the polyatomic ion itself is going to be this tightly bound group of atoms, and they're going to be held together by covalent bonds. So because we're dealing with covalent bonding here, we're going to also incorporate it into this unit. So the vast majority of our polyatomic ions were collections of nonmetals. Again, this group is going to be held together by covalent bonds. And the big thing is that they behave as a unit. So right, remember they all stick together, they move together when they form these ionic bonds later. But the polyatomic ion itself is going to have either a positive or negative net charge. Remember, our net charge just means our total charge here. So when we think about how we write the structural formula for our polyatomic ions, it's very, very similar to what we just did for molecular compounds. The only thing now we have to do is we have to factor in additional electrons that are the result of our charge. So if we have a negative charge, that means we have to add electrons. If we have a positive charge, what that means is we have to subtract electrons. So just a quick review from the last unit. The big difference is when we go about writing the structural formula, our formula is going to be between two brackets, and we're going to want to write the charge of our iron in the upper right-hand corner outside the bracket. So this is going to be one small last step we'll have to include at the very end. So what we have is when we look at these rules for how to write the structural formula for a polyatomic ion, the rules are pretty much the exact same. Only new things, we're going to add in a couple things that we're going to have highlighted in bold here. So when we try to figure out how many electrons we have to add or subtract, we're going to be basing that based off of the charge of our ion. So if we have a negative ion, we want to add electrons. If we have a positive ion, we're going to want to subtract that number of electrons from our total. So our total number of valence electrons is going to be dependent upon what each atom brings to the table, as well as what that charge brings to the table. From there, our next step is going to be connecting all of our atoms together using single bonds, just as we did previously. From there, we have to figure out, does each of our atoms have a full valence electron or full valence shell, satisfying that octet rule? If they do not satisfy the octet rule, then we have to go back and replace our double and triple bonds. We use them to replace with some of our single bonds. Again, only now differences are final steps here. For our polyatomic ions, we're going to want to put brackets around our structural formula, and we're going to put the charge of that ion that's been given to us in that upper right-hand corner outside the bracket. So really, when we think back to the rules, the only thing we're changing is now we have to factor in that there's going to be additional electrons or less electrons to the charge. Or we want to put a bracket around our final formula, and I want to put the charge in the upper right-hand corner. So if we go to walk through those steps here, we're going to look at nitrate, so NO3 minus. Again, this is one of our polyatomic ions we can get from the back of our periodic table. And we'll begin by saying nitrogen, because it's in group 15, it's going to have 5 valence electrons. So that means it's going to need 3 more. We'll look at our first oxygen. It's going to be in group 16, so it's going to have 6 valence electrons, which means it needs 2 more. Again, we're going to repeat that process for our remaining 2 oxygens as well. So, has 6 valence electrons and needs 2 more as well. We have the same exact thing for our last oxygen. And then the final thing, we have to now add in the number of electrons due to our charge. We go back to our formula for nitrate. We see that we have a charge of -1. So our -1 charge tells us we're going to have to add 1 electron. So when we think about the total number of valence electrons, we're going to have 5 plus 6 plus 6, plus 6, and then since we're adding that 1 electron due to our charge, a plus 1, going to give us a total of 24 electrons. All right, so again, as I go to write the structural formula, because nitrogen needs 3 compared to the 2 that oxygen need to have to satisfy the octet rule, we're going to put nitrogen in the middle. What we're going to do is we're going to have an oxygen off to the left, or sorry, off to the right. It doesn't make a difference if we put this next oxygen either up or down. I'm just going to put it below. Then we're going to have our final oxygen off to the left here. So again, out of the 24, we've taken care of 6 of our electrons. I'm going to go in and first fill in the lone pairs for our oxygens. So we have 6 electrons taken care of right now. Now have 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So as we go, again, we want to double check, make sure that we have satisfied the octet rule for each of our atoms here. If we look at this oxygen, we have 2 from the bond, 3 lone pairs for a total of 8 electrons. That's good. Similar thing, 3 lone pairs, 1 bond, 3 lone pairs, 1 single bond. The place where we run into issues though is with our nitrogen here. That's right, our nitrogen only has 6 total of electrons from these 3 single bonds. It does not have the full 8 it needs. So what that tells us is we're going to need to add in a double bond here. So what I'm going to do is I'm going to make a double bond between nitrogen and the oxygen on the bottom. Again, it doesn't matter which oxygen we choose. For right now, I'm just going to use the one on the bottom. Just going to have our nitrogen in the middle, single bond with oxygen on the right, single bond with oxygen on the left, but now we're going to draw in a double bond to the oxygen down below. So right now we've taken care of a total of 8 of our electrons here. We're now going to add in 9, 10, 11, 12, 13, 14. So we're at 14 right now. This bottom oxygen only needs 4 more electrons. So we have 15, 16, 17, 18. Go over to the left. 19, 20, 21, 22, 23, 24. So we've taken care of the 24 electrons we have in total. And now if I go through and look at our individual atoms to see if they satisfy the octet rule. We're going to look at this oxygen on the right. We have 1 single bond with 3 lone pairs. That gives us 8. We have a double bond with 2 lone pairs. Also gives us 8. Oxygen on the left, we have a single bond with 3 lone pairs. That takes care of our 8. And if we look at now our nitrogen in the middle here, it's going to have a total of 8 electrons due to these covalent bonds. So that looks good. So all I'm going to do is redraw that structural formula. And now if we think back to the steps we had at the very end, so once we have our finished structural formula, we want to put brackets around it. And then the last thing we want to do is we want to put the charge in this upper right hand corner outside of our bracket. So we have a charge of -1. So all we're going to do is put a minus sign at the top right there.